You are live on Teams. Don't swear. You can swear. And I share the screen. And can you see the screen? Yes, fantastic. And I got reminded Moodle attendance, and I want to say something about it because apparently there has been a little bit of a misunderstanding. The attendance is important, and I want you all to register your attendance. It's not something that I see as a sort of an optional thing. We have to follow attendance because if students don't register their attendance, then this is very often a first sign that things are not going smoothly. And if we catch things early, then it's not a big problem. So we need everybody to register their attendance. This is really mandatory. And for Tier 4 students in particular, if you fall below a certain threshold of attendance, then the university has no other option but to withdraw your sponsorship. Basically, for Tier 4 students, if you do not register attendance, then you could be kicked out of university. I am following up on the practical thing because my understanding is that the demonstrators are registering the attendance. And again, that is one of the things that we really want to make sure that students get, because these practical skills are really something we think are important. So we would like everybody who is doing the practicals, who has been sort of allocated practical spaces, and I know not all programs do the practicals, but those students who do the practicals. Oh yeah, hello. Nice to hear you. Good, thank you. Those students who do the practicals really need to register, and if there's a glitch, then we need to sort that out. So please, please, please make sure that you record your attendance. If you forget on one occasion, it's not the end of the world, but we can't give you attendance sort of after the event. And it's really the onus is on you to make sure that you do it. Okay, and somebody is still open. Can people please mute? Or am I hearing things that nobody else is hearing? Hello, can you please mute? Was it a yes? Okay, let's get started because we have a BI 308 session. He speaks vibrator. And I don't want any comments about that. Okay, so can we please mute? Dylan, Thorn, mute your mic. I'm reading out. Don't know whether this is philanthropic. Okay. Let's get started. In yesterday's session, I talked a little bit about accuracy and precision, and we started to talk about the measurement of central tendency. And I don't think I gave you the name for that. And central tendency is basically where we try to figure out what is sort of in the middle. And I showed you the mean. We talked about the median. That's the middle number. And another very common measure of central tendency is the mode. And I guess you all know what the mode is when you have a series of data points. Do people know what the mode is? Mode is the number that turns up most frequently. It's the most common number, absolutely. And then we also discussed a little bit the measure of dispersion. And that actually can be different things. One that we didn't discuss because you do it before GCSE would be the range. Does anyone know what the range is of a series? Absolutely. It is the highest number, minus the lowest number. Absolutely right. And then we also discussed the variance. And we will carry on with that. So I gave you the example. We catch 3 blind mice. Oh, okay, I better not sing. And we measure their lengths. So we measure in centimeters. And I think we've got 14, 16, and 18 centimeter length. Exactly, yes, it's them mice. We calculated the mean, and I gave you the equation for that. The equation for the mean would be xi divided by n. That's the equation for the mean. And basically, it just says add up all the xi's. So that would be x1, that would be x2, that would be x3. So add them up and divide by the number of observations. And we got for this a mean of 16 centimeters. And the variance actually tells us, to a certain point, how spread out the data are. And I gave you the equation for that as well. I told you we calculate the difference for each data point from the mean, but we have to square it and divide by the number of observations. And when we do that, we get basically, let's quickly do that. We have 14 minus 16 squared plus 16 minus 16 squared plus 18 minus 16 squared divided by 3. And that gives us, when we do the square, it gives us 8/3 for the variance. That is the spread. Now, question for you. What is the unit for the mean? I've already written it down, but just to make sure that we are all on the same page. What's the unit of the mean in this case? Yep, centimeter, that's absolutely right, centimeter. What is the unit of the variance? What's the unit of the variance? And that's the equation here. That's the variance. It has units. It is actually centimeter squared. Why? Because here, 14 minus 16, here we have the unit centimeter in it, but we square it. Yeah? So the unit for the variance is centimeter squared. And that makes it really unpleasant to work with, because we've got a mean where the unit is in centimeters, and now we've got a spread where the unit is in square centimeters. So what can we do? We can actually take the square root of the variance and this then is actually has a special name. It is called the standard deviation. So the standard deviation is the square root of the variance, also sometimes abbreviated as SD, or I prefer the abbreviation STDEV, standard deviation, because that is actually the function in Excel that you can use in order to calculate a standard deviation. So if we have in our example here, the standard deviation that we had would be the square root of 8/3. Let's take the unit with it, square centimeter, and that would give us a standard deviation of 1.63. And what's the unit? What's the unit of the standard deviation? Centimeters. Exactly. And you see, the nice thing about that is that somebody is paying into the pizza fund. Can you please mute yourself? I would be very grateful for that. I know that people are on the watch list or on the watch. Okay, so what you see is that the standard deviation and the mean have the same unit. And I would say if things have the same unit, life is good. We don't have to worry about it. Now, what I'm going to do with you now requires a little bit of rethink for you guys. Because the eagle-eyed amongst you will have spotted that I religiously write out things: standard deviation, variance, mean, observations, all these things. And I can assure you, this is not me. This is not me. I like to use abbreviations. So there must be a reason why I don't use any abbreviations. And there is. What we're going to do now is the foundation for all of statistics and data analysis that we are doing. So please stay with me for a few minutes and hopefully things become clear. Okay, we have collected data 14, 16, 18 centimeter for specific purpose. So these are our mice. And what are we going to do with these data? Now, I can reveal the reason why I have chosen these data is because my sister phoned me from Germany and said, look, it's COVID. I need to get some money in. We have problems with mice. So I want to manufacture live mousetraps. She doesn't want to kill the poor little mice. I want to manufacture mousetraps. And I said, okay, good. And she said, well, there's a problem. I don't like mice, although she is, manufacturing mousetraps. How long is a mouse? Because she explained to me, if I make the live trap, so no mice were killed, if the mousetrap is too small, then I won't catch any mice. If the mousetrap is too big, I waste material and that cuts into my profits. So how big is a mouse? And I said, to be perfectly honest, I don't have a clue. And maybe it depends on, where you catch them or what kind of mouse it is and all these things. So we thought about what we can do to answer her question. So I caught these 3 mice. Actually, I let my feline housemates do the job. And the mice were in a not such a good state afterwards. But at least I could do some measurements. And what I am doing here is...
That is really cute. What's Ryan?
Yeah, I know. And Ryan is so cute.
Oh shit, I need my... Just got crushed by the door.
Please tell us a little bit, tell us more about your love life.
And I have loads of work to do.
Yeah, I know that's a problem.
Yeah.
Yeah. And also the multiple choice quiz.
They don't ask me anything.
No.
Mute your mic.
Callum,
Hello.
there's another clown. There's another clown. Some guy just unmuted his mic and was like, mute your mic. Do you have another clown in the room today? Oh no.
Oh gosh,
Oh, yeah.
you can't make that up.
Thank you.
Bye bye.
That's cool.
Oh, cool, hey?
It's basically just standard deviation and like
Yeah,
you probably don't even need to watch this film.
no. Yeah, well, if you know that already.
Yeah, it's funny, isn't it?
Mike, you know, said mute yourself, please.
In a bit. Have fun being quiet.
I would like to mute Maya Hutton, but unfortunately, if I leave the screen, I will not be able to get easily back and I have to start the whole thing again. Fantastic, we are now back. So, I've measured the mice, and what this actually represents is a sample. I took a sample of basically lots and lots of mice that are living around here, where I live, somewhere in East Kent. So what we have is actually we have a huge population of mice. And so that's my population. Of mice. And I can't measure all the mice here in wherever I am. I can't measure all the mice in the UK. I can't measure the mice in Germany, for example. Not all of them. I don't even know how many mice there are. How many mice do live in in the UK? Any idea? A lot, yes. Ask Siri. 200 mice. Now that's what my cats bring in a year. So what I've taken is a small sample here. So that's the sample that I've taken. And this sample has a mean. And we calculated that mean. And it was 16 centimeters. So the mean, and we had a standard deviation. Standard deviation, what was it? 1.63 centimeters. So we had a sample mean, that's sort of the center. And we have the spread, that's the standard deviation here. Now, what we can do with this sample is we can make an estimate. Make estimate we can sort of say, hopefully these 3 mice were representative of all mice. And we can make an estimate about the population mean. About the population mean. And we can say from our sample, which is the mean 16 centimeter, we also assume that the population mean is also 16 centimeters. Right? Does that make sense so far? So we basically infer from our sample to the population. So we say the population mean is 16 centimeters. Now, actually, what would be good, because we are talking actually about 2 very different things. One is a sample mean and the other one is the population mean. The sample mean, that is what I've calculated here. The population mean is something that I probably will never find out, because for the population mean to get, I would need to measure all the mice. And therefore, to indicate that there is a difference between these things, when we talk about a population mean, we abbreviate it with the letter mu. So that is mu, that means population mean. That's the population mean. Population mean. That is just the abbreviation for the population mean. And we said that is probably the same as the sample mean, because the sample mean, that is what I can measure. For the sample mean, I use a different abbreviation, and a sample mean is abbreviated, or has the abbreviation as an X with a line on top. This is also called X bar. So when you see X bar, you know it is the mean of a sample. When you see the mu, you know it's the mean of the population. Okay? So far, so good. Now, what about the standard deviation? What about the variance? We determined a certain standard deviation. That's the standard deviation. Let me take a different color. So that's our standard deviation. That's the variance. That's the spread in our sample. And the abbreviation for a sample, for a standard deviation, let me write that properly. For a standard deviation, when we use a sample, the abbreviation is lowercase s, which is very imaginative because that stands for standard deviation. Now, big question for you. Do you think the standard deviation S is the same standard deviation for the population? People say no. So our S, that's the sample standard deviation. What would you say is the standard deviation for the population? Is it larger or smaller than the sample? If you look at this picture that I've drawn, is the population standard deviation larger or smaller? So if you compare that, if you compare our sample standard deviation, if you compare that with the population standard deviation, which would be this one here, that would be the spread. So the sample standard population is always smaller than the standard deviation for the population. Standard deviation for the population. And because, as you can imagine, with the sample, we just get a small part of it, whereas the true population standard deviation is much bigger because there might be more mice with different sizes around. The abbreviation for the standard deviation when we are looking at the population is the Greek letter sigma. So that's sigma. So we have S for when we are looking at the sample, and when we are looking at the population, we have sigma. And you can easily find or figure that out because everything related to population, has Greek letters. Whereas everything related to the sample has just normal letters apart from this X bar. So when I talk about mu and sigma, you know that I'm talking about population. Now let's rewrite our equation for the variance. Let's use the population variance. And we know that the population variance is, if we are using the population variance, if we want to get the variance, we just simply have to square the root. So the population variance is the population standard deviation, squared, which could be abbreviated as sigma squared. So we can write sigma squared, we can write this as the sum of xi minus, now we have the population mean, because it is a population, so we write this as mu squared divided by n. Okay? Does that make sense? This is sort of just some kind of terminology alert. Excellent. We can also write the mean. This would be xi divided by n. And n represents the number of observations that we have. Okay? Now we just said we know that usually when we are working with a sample, we get a standard deviation, so a sample standard deviation. And very often what we want is we want to estimate the population standard deviation. Oops. We want to estimate, let me write it like this, estimate the population standard deviation. Standard. So we get our sample standard, S equals a number, but we know that the population standard deviation must be larger than the sample standard deviation, what we just measured. How do we do that? How can we estimate the population standard deviation? A square outside the xi in the brackets, not in this case. The square is here when we're talking about the variance, but not when we're talking about the mu. So how can we estimate our population standard deviation if we've only got the sample standard deviation, what we just calculated? And we know that when we measure our sample, that the standard deviation is smaller than the original population. Now it turns out that a very, very good estimate for that is if we just make our estimate for the population standard deviation a little bit larger. So how can we do that? We can actually do that by saying, right, we have our sample here, and we know how this is calculated. It is xi minus x bar. That's the sample mean. Sample mean divided by the number of observations but we want it a little bit bigger now. We say n minus 1, because if we divide something by something smaller, then the something becomes bigger. And I'll show you that in a minute. So this is actually, and I think I want to write that down, the sample standard deviation. And it's getting a little bit confusing, and I'm fully aware of that. That is the sample, I'm sorry, that is not the sample standard deviation. Sample, let's call that the sample variance for that. Sample variance. has this equation here, and this is an estimate for the population variance. It's really deviating, isn't it? It's an estimate for the population variance. So what does that mean in practice? I'm with currently in the variances. So let's say we have 14, 16, 18. That's our sample. Now I calculate the mean of the sample. That's x bar equals 16, right? That's the mean. And I want to make an estimate for the population. And yeah, I want to make an estimate for the population mean, and that is also 16. So the means are both the same for population and the sample. That is estimate. Mean, that's the population mean, which I get from my sample mean, from this x bar here. What about the variance of the population? I don't know the variance of the population, but I can estimate it by using the equation xi minus x bar divided by n minus 1. So let's do that. We have 14 minus 16 squared plus 16 minus 16 squared plus 18 minus 16 squared divided by, so what is n minus 1? You're absolutely right. N minus 1 in this case is 2. So let's do the calculation. So here we have, what did we get for that? 8 divided by 2. So this variance would be 4. When we just simply looked at the variance of this part here previously, we got a variance of 8/3. So just looking at this variance here would be 8/3, and that was 2.67. But when we are looking at the variance of the entire population, we get a variance of 4. And it has, of course, centimeters squared. So we are talking about population and sample variance and standard deviations here. So we have two different variances. We also get two different standard deviations. Here the standard deviation would be 2.67, which is 1.63. And here the standard deviation would be the square root of 4, which is easy, which is 2. So our estimated population standard deviation is equals to 2, whereas our calculated standard deviation, that is 1.63. N minus 1 is a sort of an adjustment factor that allows us to use what we calculate in our sample for the population. So whenever we are trying to estimate a population, standard deviation, we use the equation xi minus x bar squared divided by n minus 1. We estimate the population standard deviation from a sample. That is what this term actually says, right? We estimate the population standard deviation. Oh, sorry. And we need to take the square root. Estimate the population standard deviation from a sample. Therefore, we use this equation here. Can I please nail that into your brains? We estimate a population standard deviation from a sample. And therefore, we use this equation here. Does that make sense? Everybody's quiet. Have I shocked you? So we use our measurements 14, 16, 18. We use these measurements to figure out what is the population variance or population standard deviation. These measurements are the little sample here. And in order to do so, we calculate the variance of this one here. But instead of dividing by n, we now divide by n minus 1, because that gives us an estimate for the population standard deviation or population variance. And the really, really mean thing is that all the statistics books and for one reason or another, I don't know why this is, they tell you that when we use this here, estimate population standard deviation from a sample, this is actually called, wait for it. This is a very good question. Why not n minus 2? It turned, there are some mathematical considerations why it is n minus 1. One can prove that, but I think that would go a little bit too much into detail. So wait for it. This thing, as I said, let me do this in a nice color. This is the equation when we have a sample. This is the important equation. When we have a sample, we can estimate the population standard deviation with this equation here. And guess what textbooks and statisticians call this thing? This estimate of the population standard deviation from the sample. What do you think they call that? What is the most confusing term that you could think now, apart from tortoise? You could call it tortoise, but that wouldn't make sense at all. You would actually, Edith, you would think it is called the population standard deviation. You would think it is called the population standard deviation, because that is what we do. We estimate the population standard deviation from a sample. You would think it is called population standard deviation. And I said, it's going to be confusing because it's called, absolutely right, standard sample standard deviation. And it's abbreviated with the S. Although it is an estimate for the population standard deviation, it is called sample standard deviation. So the sample standard deviation, which gives an estimate for the population, is S equals square root of xi minus x bar squared divided by n minus 1. That is an estimate for the population standard deviation. If we already have the entire population there, we have the standard deviation for the population. We don't need to estimate anything because we know it. We know what this would be. Oops, nice line here. For the population, when we already know the population, xi minus the population mean squared divided by n. This is no longer an estimate for the population standard deviation. That is actually the population standard deviation. When we do the estimate for the population standard deviation, we divide by n minus 1. When we know already the data, then we just simply divide by n. And if anyone is still not confused, it gets even better, because there is another term which I just want to quickly introduce to you, because we need to work with that next time. This is called the standard error of the mean, very often abbreviated as SE or sometimes SEM. And this is defined as the estimate for the population standard deviation, which is the sample standard deviation, S, divided by square root n. So standard error is S divided by square root n. And I fully appreciate things have moved on a little bit from A levels. To be absolutely fair, usually you would not necessarily deal with the population standard deviation because that's trivial. Usually you don't have a population standard deviation and you will always try to figure out what it is. So most of the time you would use this equation here, where you divide n by n minus 1. So this is the standard error of the mean, sample standard deviation divided by square root of n. And with that, I leave you in peace. Don't worry, we will do some exercises, we will do some calculations, and the next practical that we have in week 5 will really focus on these terms. So is the estimate population standard deviation the same as the sample standard deviation? Absolutely right. Absolutely right, Louis. The estimated population standard deviation is the sample standard deviation. And there are two standard deviations. One is the calculated population standard deviation, where you divide by n, and one is the estimate for the population, where you divide by n minus 1. So in this case here, I know the population standard deviation. I don't need to estimate anything. In this case here, I need to estimate it, and therefore I divide by n minus 1. If you are talking about variance, yes, you would use sigma squared. So if you just want a standard deviation for your sample, that's a very good question. I mean, what is it that you want? Do you just simply want to know what is the sort of the spread of the data in the sample? Do you just want to know what the spread is in your sample? What you then would do is you just simply say, oh, my sample, actually, I treat my sample like the whole population. I don't need to do an estimate because I'm perfectly happy with this here. And I draw big circles around it. I treat this as a population. Then I just simply use this equation here, if I just want the spread of that. But if I try to figure out what actually is the underlying population standard deviation, then I would use this equation here. And Jamie absolutely hits it on the head. If you have all the data and you don't want to do any estimate, you divide by n. If you want to make an estimate for a bigger thing, then you divide by n minus 1. Be careful. The standard error of the mean will usually only apply to when we do estimates. So therefore, you have to use the S. So you have to use basically square root of xi minus x bar squared divided by n minus 1 divided by square root of n. You can't really replace the S and the standard error of the mean with a sigma, because the sigma would be you divide by n. Time's up. I'm sorry, this was really hard going, but I promise you it will get easier when we do concrete examples with that. So thank you very much for watching. And for those of you who are doing BI 300, I shall see you from 5 to 6 when we are going to talk about amino acids. Thank you very much, and think about it. There's lots of stuff on YouTube. So fish around a little bit so that you really understand the whole concept. It's really important to me. Thank you very much and see you later. Take care. Bye-bye.